Infrared or IR spectroscopy is a technique used to characterize covalent bonds. Molecules with certain types of covalent bonds can absorb IR radiation, causing the bonds to vibrate. An IR spectrophotometer can measure which frequencies are absorbed. This is generally represented with a spectrum of percent IR radiation transmitted through the sample at a given frequency in wave numbers. In this type of spectrum, the peaks are inverted, as they represent a decrease in transmitted light at that frequency. The absorbed frequencies depend on the identity and electronic environment of the bonds, giving each molecule a characteristic spectrum. However, each type of bond will absorb IR radiation within a specific frequency range and will have a common peak shape and absorption strength. Peaks can therefore be assigned to specific bonds, allowing identification of an unknown compound from the IR spectrum. This video will illustrate the characterization of an unknown organic compound with IR spectroscopy and will introduce a few other applications of IR spectroscopy in organic chemistry. A covalent bond between two atoms can be modeled as a spring connecting two bodies with masses m1 and m2. This spring has a resonance frequency, which in this case is the frequency of light corresponding to the quantum of energy needed to excite an oscillation in the bond at that same frequency, but with even greater amplitude. The resonance frequency of a bond depends on the bond strength and length, the identity of the involved atoms, and the environment. For instance, a conjugated bond will vibrate in a different frequency range than a non-conjugated bond. The resonance frequency also depends on the vibrational mode, which is the oscillation pattern of the atoms within a molecule. The most common vibrational modes observed by IR spectroscopy are stretching and bending. Linear molecules have 3n-5 vibrational modes, where n is the number of atoms, and nonlinear molecules have 3n-6 vibrational modes. IR spectrophotometry is primarily performed by shining a broad-spectrum light source through an interferometer, which blocks all but a few wavelengths of light at any given time onto the sample. An IR detector measures the light intensities for each interferometer setting. Once data has been collected over the desired frequency range, it is processed into a recognizable spectrum by Fourier transform. The sample can be gaseous, liquid, or solid depending on the construction of the instrument. For a standard detector, gases and liquids are placed in a cell with IR transparent windows, and solids are suspended in oil or pressed into a transparent pellet with potassium bromide. The IR light is then directed through the sample to the detector. An alternate method for solid and liquid samples is attenuated total reflectance, or ATR. In this method, the pure sample is placed in contact with a crystal surface. IR light is then reflected off the underside of the crystal into a detector, with the absorbed frequencies reflecting more weakly. The sample doesn't need to be processed first, as the light does not travel through it. Now that you understand the principles of IR spectroscopy, let's go through a procedure for identifying an unknown organic compound using the ATR sampling technique on an FTIR instrument. To begin the characterization procedure, turn on the FTIR spectrometer and allow the lamp to warm up to operating temperature. Ensure that the ATR crystal is clean. Then, with no sample in place, use the spectrometer software to record a background spectrum. Next, obtain a solid sample of an unknown organic compound and note its appearance. Using a clean metal spatula, carefully place the sample on the crystal surface. Alternatively, for liquid samples, a pipette is used to transfer samples to the crystal surface. Carefully screw down the probe until it locks into place to fix the sample against the crystal surface. Then collect at least one IR spectrum of the unknown sample. After data collection has finished and the background has been subtracted, use the analysis tools in the software to identify the wave numbers of the peaks. When finished with the spectrometer, remove the sample and clean the probe with acetone. Save the spectra, close the software, and turn off the spectrometer. In this experiment, the unknown sample may be one of 10 organic compounds, each with 5 characteristic IR peaks. Based on the phase and visual appearance of the unknown, 8 of the possibilities may be eliminated. The spectrum from the unknown compound shows a wide peak near the 3300 wave number region, indicative of either an OH or NH stretching absorption. The peaks to the right indicate the presence of carbon-carbon double bonds and carbon-oxygen bonds. Of the 2 remaining compounds, only one has an OH group, so the compound is phenol. IR spectrophotometry is a widely used characterization tool in biology and chemistry. Let's look at a few examples. In this procedure, FTIR spectroscopy performed with the ATR method was used to obtain IR absorbance images of tissue by introducing a microscopy component into the instrument. Each pixel in the image had a corresponding IR spectrum, allowing determination of the molecular composition of the tissue with excellent spatial resolution. The tissue image could also be displayed at different frequencies to visualize the distribution of molecule types throughout the tissue. The molecular vibrations of peptide groups in a protein are affected by protein conformational changes. By monitoring a protein sample with StepScan FTIR, which has a temporal resolution on the order of tens of nanoseconds, protein dynamics can be monitored via the changes in their absorbance spectra. The data can be presented as individual spectra or as 3D plots of intensity, frequency, and time for peak identification and further analysis. You've just watched Jove's introduction to IR spectroscopy. You should now be familiar with the underlying principles of IR spectroscopy, the procedure for IR spectroscopy of organic compounds, and a few examples of how IR spectroscopy is used in organic chemistry. Thanks for watching.